You've got so many papers in so many areas that it's a little hard maybe for somebody to kind of stand back and say, what are the big themes? What would you say are the biggest themes?
Some of the themes early on came from problems at Bell Labs, for example. So early on in the kind of middle 60s, I was doing a certain amount in scheduling theory. Scheduling theory, you have a certain number of jobs, a certain number of machines, and each job has a certain amount of time and certain requirements that it must be done before others can be finished, started. And the question is that Bell Labs in those days was one of the software contractors for the ABM, the anti-ballistic missile system. And when you have a fleet of incoming missiles, you have to decide fairly quickly on what to do about it. Whose are they? Where are they headed? How should I respond? And they had programs, and they noticed that if they changed the order that they tried to do something, it would finish sooner than other times. It depended on the list. The question is, how bad could that variation be? And it turns out that kind of examining that problem, you can then come up with the idea of saying, well, it might be very hard to get the best possible list. In fact, it's known nowadays to be NP hard to do it. But you could say at least how this algorithm comes within a certain guaranteed factor, like at most 50% worse or two-thirds worse. And this was kind of worst-case analysis, one of the first examples. It's kind of a big area in approximation algorithms to try to decide, sure, you can't get the optimum, but here's an algorithm that's not too bad, and you come within 10%. Maybe 10% is fine, you see. Then later on, I ran into people who are working on Ramsey's theorem. Now, Ramsey's theorem is basically based on the philosophy that if you have a large, complicated structure, then within that structure, there often, inevitably, is some more well-defined substructure. I think in the movie A Beautiful Mind, Russell Crowe, playing John Nass, points up to the stars and say, look at a pattern, look at a square, look at up there, and oh, look at this, almost a square. Well, Ramsey theory kind of makes that very precise, and it's been a very active field now. And of course, I and Bruce Rothschild and a guy named Klaus Leib at Berkeley proved kind of very general Ramsey theorem that kind of implied kind of most all the known ones at that time. And then people wonder, well, the canonical example is the theorem of van der Waals in 1927, that if you take the integers and you color them in two colors, one of the colors must have arbitrarily long arithmetic progressions. And the question is, if you have more colors, is it true? Or if you just have a bounded number, how many do you need before you're guaranteed to have a k-term progression? And that's been the thrust and the motivation for a lot of very recent work of Terry Tao and Gowers and Ben Green and people like that to try to get precise estimates on how fast these functions grow.